So we're going to talk a little bit about the introduction to linear transformations today. So just this again is just to give you a little bit of an introduction into stuff that we're going to start talking about tomorrow in class. So basically, I want to give you the definition of linear transformation, a couple of examples, one with a little bit of geometry to it, so you can kind of hopefully get a feel for what we mean by linear transformations, and then a couple of properties that all linear transformations have. And then, like I said, I'm going to spend class time actually doing more examples of these things and doing a little bit more explanations. The whole goal of this topic, by the way, is to try to get these linear transformations to look like they're going from, instead of arbitrary vector space to arbitrary vector space, really our goal of this is to make it look like a transformation that goes from the reals to the reals. So some Euclidean space Rm to another Euclidean space Rn. Okay, so let's do the definition. So V and W here are going to be vector spaces, and we're going to have a function that has a domain of V and a codomain of W. So then T is called a linear transformation if, whenever we have any two vectors from V and any scalar C, the function satisfies these two properties. So the first one is that the transformation will break up over sums. So the transformation applied to U plus V is the same thing as the transformation applied to U plus the transformation applied to V. Now, just before we go on and talk about the next part, remember when we talked about doing vector spaces early, we had opportunities to redefine what the plus sign meant, right? So this plus here is taking place in V. This plus is taking place in W. So somehow the linear transformation has to preserve that structure. And what I mean by preserve that structure is it doesn't matter if you add first and then do the function and do the addition in V, or do the function and then do the addition. Okay? Remember back again, addition can be funky when we talk about vector spaces. So there's some structure saving that's going on here. Okay, the other one here is that if I take the transformation applied to a scalar times a vector, so a C times the U, I can pull the C out in front. And again, just like I mentioned in the first property, there's some structure saving going on. This scalar multiplication is taking place in V. This scalar multiplication is taking place in W. And again, when we did vector spaces arbitrarily back in chapter 5, we know that we can redefine, in certain instances, our scalar multiplication to be different than what we're used to. Now, that being said, most of the examples that we're going to be doing won't involve crazy addition or crazy scalar multiplication. But I just want you to notice that this really is talking about a structure-saving idea. If you go on to take abstract algebra, you're going to see this kind of structure-saving idea again. So keep that in mind. All right, so let's do an example so you actually get a feel for what's going on here. So I'm going to define my function going from R2 to R3. And all we're going to do is take the vector xy and map it to the vector xy and then an x plus y. So your third component here in R3 is just going to be the sum of the components in R2. Let's go through the definition and verify that we really do have a linear transformation. So remember, it says that if I add first and then apply the function, is the same thing as applying the function and then adding. So here, I'm doing the transformation applied to the sum of two vectors, and this is what the sum of those two vectors would be. Here's the transformation applied to those two, to that particular vector, right? It says take the first component, make it the first component in the output. Second component, make it the second component in the output, and then add the two components together to get the third component in the output. Now let's just play around with the algebra. Here I'll just flip around the y1 and the x2. I can split that into the sum of two vectors. Not too hard to see, right? Just taking the first parts off and taking the second parts off and splitting it into two vectors. And we really do see that that's the output for the first vector and the output for the second vector added together. So we really can distribute, if you will, the transformation over the sum. Let's check the scalar multiple as well. So scalar times the vector, let's just call it xy here so we don't have to deal with the subscripts because I'm only talking about one vector here. Scalar multiplication, just distribute the c. Again here, this tells us to take c, the first component, the second component, and then add the two components together for the third component. And in that case, I can factor out the c. It's not too hard to see that if I take cx plus cy, I can factor out the c. And then here, that's just popping out the c out in front, and that really is the scalar then times the function. So according to the definition, t is a linear transformation here. So let's look at the geometry of this a little bit, because I think that's a little bit, may help a little bit help you understand a little bit better what's going on. Okay, so again, we're taking the image from R2, which would be, here would be your coordinate plane, the XY plane, if you will. This is an image of R2 in R3. And then this purple piece here is just a piece of the output. So here was the vector 1, 0. 1, 0, 0. But think about it as the vector 1, 0 in R2. And here's the vector 0, 1 in R2. Okay, so this one that's slanted this way, this is the image of this vector under the transformation. So notice that it's the vector 1, 0, 1. This vector here is the one that is the image of the 0, 1, 1. And what I've represented here is this unit square, this blue square. The image of that is this purple, well, I assume parallelogram, but it's probably a rectangle in R3. Okay, so definitely a parallelogram, but it looks like a rectangle. So notice that when you have a linear transformation from a geometric standpoint, at least for Euclidean spaces, from a geometric standpoint, it preserves the relative shape. And what I mean by that is, notice I didn't twist it, right? I might have stretched it, I might have what's called shear it, but I didn't twist it, I didn't bend it. It keeps that same linear shape. So to give you a little bit more illustrative shit of what I mean by that, let's just look at this from straight down. Notice if I look straight down from the top, so going right down the z-axis, notice that purple landed right directly on top of that original unit square piece. So that's what I mean by it. It didn't fundamentally change the shape of it. I can look at it like I think about it as a shadow. I can look at the shadow of it, and that shadow really does look like the original piece. Okay, so when we're doing a linear transformation, it might rotate it. It might turn. What I mean is turn it, but it won't twist it. Notice I don't have a bent shape here, right? This purple thing is a nice flat shape. It's not bent. It's not looking like some sort of a paraboloid type of thing, right? Having parabola cross sections or something that's bent, right? It's still flat. I started with a flat thing. I ended with a flat thing. So linear transformations from a geometric standpoint aren't changing the fundamental shape. It might change its look a little bit. It might rotate it to a different spot, those kinds of things. But it might stretch it, it might shrink it, but it's not bending, it's not twisting, it's not breaking it apart, okay? So that's kind of the idea for geometrically what we're talking about with linear transformations. Okay, going back to the presentation now. Let's look at another transformation that's not a lot of geometry, but it is a familiar idea. So let's say we want to take our set of polynomials with degree n and map it to a set of polynomials with degree n plus 1, where the transformation is defined as the integral. Okay, so you can see why the power would go up by 1, right? When we integrate a polynomial, we would add 1 to our exponent. So this notation maybe look a little bit funny, but remember that if I want to integrate and then plug a variable back in, I need to have a different variable here for my integration variable. All right, so let's see why this is a linear transformation. Well, the transformation applied to the sum would be put the sum into the integral. From calculus, we know that we can break integrals up over sums. And that really is just the transformation applied to each polynomial. Same thing here with the constant. Transformation of the constant times the polynomial is the integral. I can pull the constant out in front of the integral as well. And that's just the constant times the transformation. So this really is a linear transformation, without any doubt. And what is your image here of this linear transformation? Well, when we do the integral, think about when you do an integral of a function. Well, I would do the antiderivative, and then starting at 0 here means that I really am just putting in zeros for all the x's for my lower limit of integration when I integrate, which means I'm getting a constant 0. So this transformation sends a polynomial to its antiderivative, which is certainly what the integral is doing. But the 0 being that lower limit of integration means that the constant term is going to be 0. So that's what this. So instead of doing an arbitrary antiderivative with the plus c on the end, this linear transformation would just say, well, don't worry about the plus c. Literally what it's doing. Other types of calculus linear transformations, well, anything that breaks up over a sum and constants pull out would work. So the derivative operator, taking the derivative of a function, that would be a linear transformation. Doing limits would be a linear transformation. It would be a linear transformation from the functions to the real numbers. And so, of course, you'd have to worry about limits existing. So you'd have to do some conditions on your functions. But those are kind of the linear operations that you've already talked about from calculus perspective, right? Things that break up over sums and where constants pull out. Now notice things like, of course, doing the sine function is not a linear transformation of anything because sines don't break up over sums. Log function, not a linear transformation. So those kind of things. Just to end this little demonstration, let's talk about a couple of properties that all linear transformations have to have. So the transformation applied to the 0 vector of v, this would be the 0 vector in v, has to be the 0 vector in w. This is an input, this is an output. But the proof technique is very, very familiar to us. Do your tried and true trick of letting 0 be 0 plus 0. Split the transformation up over the sum. And subtract the image of the transformation from both sides, and you get t of 0 is equal to 0. So from here to here, all we're using is the fact that the vector space had a 0 vector. From here to here, this is your property of your transformations. And from here to here, you're using the property that the transformation, the vector space, everything in the vector space has an additive inverse. So using those vector space axioms again. Here's another one. If you apply the transformation to an inverse of a vector, that has to be the inverse of the image. So what this says is the image of an additive inverse is an additive inverse of the image. Okay. Start with what we just proved. Of course, I can write the 0 vector as a vector and its additive inverse added together. Split it up over the plus sign. And then move this over to the other side. So not a very difficult proof at all for that. Okay. So, but again, remember that this is a structure idea, right? This one here, this is the 0 vector in V. This is the 0 vector in W. And we've already seen that if your addition is defined differently, your 0 might be defined differently. And this is an additive inverse in V. This is an additive inverse in W. So again, notice that there's a structure saving idea that goes on with your linear transformations. All right, so again, we're going to do lots more examples of this in class, and this is the kind of stuff that we're going to be talking about for the rest of the semester. It's just linear transformation ideas. So until tomorrow.